Okay, so we want to talk about herbicide selectivity and probably conclude the lectures on herbicide selectivity. Here we are going to focus on atrazine. Atrazine selectivity. This is a commonly used herbicide. Herbicide in maize. So we want to look at phase 1. They say this herbicide has entered the maize plant after application. How is the selectivity achieved in maize? So that could be phase 1. Now the structure of atrazine is like this. You have a carbon here, then you have got a chlorine. If I just do that, here you've got your nitrogen, You've got your nitrogen, and I can do this. You've got another C here, another C here. Here you've got the last nitrogen connected to that. Here there's a double bond. Again, here there's a double bond. Here there's a double bond. Here you've got a nitrogen. Again, here you've got a nitrogen. Here you've got a hydrogen. There you've got C3H5, an ethyl group. Here you've got a methyl group, which is a C2H5. Okay, let me okay, you've got an H here. Then here you've got C2H H5. Here we've got actually a 7. There's a 7 there. So this is atrazine. Now, first we want to find out what are the functional groups. Where do we get the functional groups? Was in phase 1, we used to talk about the cytochrome P450, which act upon the functional groups. But anyway, let us find out which are the functional groups. I will have to use a different color so that you can see. This position here is where we have a functional group. Again here, and also here. Now, we used to talk about the cytochrome P450. Cytochrome P450. And we said that in the phase 1, this would actually change the functional groups because of its activity. But with specific to atrazine, there's a slight difference some people say that it is not actually cytochrome P450 which is causing changes, but instead we have got this enzyme benzaxazinone, or we can just call it Dimboa. You just have to choose the one which you want, the Boa, which is quite a complex name. So this one is important in other herbicides, but specifically for atrazine, we have got the benzaxazinone, benzaxazinone. This is it. Benzaxazinone. Right. So what is going to happen is that either the Cl or chlorine, this is chlorine, an OH is going to be added under the facilitation of benzaxazinone or Dimboa to form an OH. In the next slide, I will just represent the structure of atrazine using, I can just call it atrazine, so that we don't get confused. So the first process is hydroxylation. You now know about it. Hydroxylation, where we will say atrazine with a Cl is going to form atrazine with an OH, and here we need Dimboa to facilitate this reaction. Another thing which can happen is that at this area where we have the nitrogen being joined to the ethyl groups, this position here and that position here, it requires what is known as N-dealkylation. So the next thing we are talking about is this reaction any dealkylation where we have H, then C2, five, atrazine, there's an N here. Here we are going to have an NH2, atrazine, and NH2, because this process has to be done in 2 stages in order to change what is added the nitrogen group. So we'll end up with the NH2 in the end. Let me check. Okay, I hope you are seeing something now. So we've got, are you seeing something now?
Yes, good.
Okay, thanks. Right, so atrazine can now be converted to those amines which are joined to atrazine. Of course, we could have attached them here where I've got some ticks, but we just wanted to simplify this reaction. So we've got hydroxylation, then this is the it's what we call the N-dealkylation. N-dealkylation. So as far as atrazine is concerned, in phase 1, you can have hydroxylation, a removal of the Cl, forming the OH, and then you can have removal of the ethyl groups, leaving the amine. Then we enter into phase 2 with the atrazine. Now in phase 2, We have the activity of glutathione. Glutathione activity. We also have glutathione S transferase. Or just GST enzyme. So we have got two things. And the glutathione, we can represent it like glutamate, cysteine, and glycine in short. And here we have got the reacting group, the SH. So this is the glutathione. Now, because atrazine now carries the OH, this OH is going to react with the SH the OH here and the SH here. These are going to react like so. We call this one the conjugation reaction. Conjugation reaction. Where we have glutamate joined to cysteine, joined to glycine, which forms the glutathione. And of course we have this reacting component. This is atrazine with the OH. Now we have glutamate, then the S, the sulfur, is now joined to the atrazine. Right, and from this structure, this one makes atrazine less toxic. Actually, it detoxifies the atrazine. Now, in maize leaves, we do have a lot of glutathione. That is this glutathione. This one. We have plenty of it in the maize leaves. And it protects the maize from atrazine toxicity by simply combining with the atrazine in a conjugation reaction. But this is coming from glutathione combining with the OH. But glutathione can actually go straight for the atrazine molecule and attacks it at the Cl group or the chlorine group without waiting for the formation of the hydroxyl or the OH. Because of that reason, maize is not actually affected by atrazine, although we do have some breeding lines which could be affected by this by the atrazine. We also have the products of dealkylation, which we can products of any dealkylation. Dealkylation. And we just said atrazine is now carrying the NH2 groups. The question is any glucosylation possible? Of course, the main detoxification process is glutathione joining this atrazine, and here I must also emphasize that we have a GST enzyme. I will make it short. GST enzyme facilitating this process. Glutathione S transferase. Let's go back to our question. Is any glucosylation possible? By any glucosylation, what I mean is that is sugar going to detoxify this atrazine as well. Role of sugar. Because we do have these NH2, the amine portions. So probably, I will say probably, because it's not usually mentioned that this process takes place. N-glucosylation. So atrazine with an NH2 with NH2, we can have this okay, let me write. Here we have got sugar being donated by UDP glucose. UDP glucose, and UDP is released. So we now have atrazine and glucose. Right, and here we will have this enzyme UDP glucose transferase. UDP glucose transferase will facilitate the formation of atrazine and glucose, because atrazine is carrying two NH2s. Maybe this will go twice to produce atrazine and glucose. We also know that in fact, the other question is all glucosylation possible? Because we also have atrazine carrying the OH. We know atrazine with OH can also undergo conjugation via the glutathione group. If we have some, there could also be a possibility that UDP glucose could act upon it. UDP glucose. So we are likely to get atrazine or glucose. This will give us UDP, and we need UDP glucose transferase enzyme to facilitate this reaction, which produces this atrazine or glucose. Well, this may be a possibility. Remember, this is occurring in the phase 2. Let us not forget we are in phase 2. Let us proceed to phase 3. Now in phase 3, we have the activity of malonyl coenzyme A. Maybe it gives us malonate which is going to combine with atrazine or glucose, and it probably gives us malonyl glucose or atrazine. There's also a possibility of malonate plus atrazine, which has an N here, giving us malonyl glucose and atrazine. Now these products will become part of the cell wall, or they may enter the vacuole, and that could be the end of atrazine. This product here, formed by glutathione, this one will go to the vacuole. Before we forget, this will enter the vacuole. So this is how atrazine is likely to be metabolized, probably in the plants. These processes are very fast in the maize, and hence the maize is not going to be killed. But in weeds, such processes could be slow, and the atrazine will be able to express its mode of action. It interferes with the photosynthesis, photosystem 2, and disrupt the production of carbohydrates. That is now possible in the weeds, not in the maize. So I thought we could just go through this process. In fact, when you try to do your assignment on atrazine, probably this is what we have just done. You may have to solve for the 2,4-D, which I simplified and put one functional group. Now, we now want to move on to talk about what is known as the beta oxidation. Now, some herbicides like 2,4-D are applied as 2,4-DB. This is 2,4-D. We also have MCPB, which is converted to MCPA. But the herbicide is in the form of 2,4-DB or MCPB. These are harmless, but this is toxic. So the idea is that when we apply these non-toxic substances, they get converted to toxic substances. The process of converting these forms to toxic products is known as beta oxidation. So some plants which can carry out beta oxidation and form these toxic forms, they end up dying. But the plants with a slow process of beta oxidation will survive. This is how sometimes selectivity is achieved. You apply the herbicides in a harmless form, but you leave it up to the plants to manufacture the toxic forms. And it is in the weeds where this beta oxidation is very fast. So I just wanted you to know something on beta oxidation. We can move on to something different, but still on selectivity. Here I wanted to talk about what are known as safeners. Or protectants. Now, This is important in maize and sorghum. Where we have grass weeds. Maize is a grass, sorghum is a grass. Sometimes when we want to kill grasses, we limit our options in terms of herbicides. For example, in maize, we may want to use EPTC. This could kill maize, although it's an important herbicide. But EPTC is something known as dichlomid. Now this dichlomid is a softener or a protectant. Okay, let me so it is a softener or a protectant. Protectant, right? Now the manufacturers of APTC have got to include dichlomid within the formulation. So within the formulation of EPTC, they have to put dichlomid in order to protect maize. The other example of the herbicide is this one you should know, the metallochlor or jewel. Now the metallochlor, the softener is known as the concept. Now it is now important if you are growing sorghum, EPTC is for use in maize, right? But metallochlor generally doesn't kill maize, but it can kill sorghum. So if you are going to use jewel or metallochlor in sorghum to kill grasses, make sure you have got metallochlor with concept as the protectant or the safener. If you just use dual, you are going to kill, or metallochlor, you will kill your sorghum. This is for sorghum. And this one is, you should know it, it's commonly being used. If you are growing sorghum and you want a grass killer, please look for the metallochlor with the concept. Then we have got anachlor. Orolaso. Anachlor has got a safener called flurazole. But what is important is not to know really the names of safeners or protectants, but to know whether that herbicide contains a safener, and usually it's on the labels. We also have acetachlor, a grass killer with this safener oxabetranil. Oxabetranil. Now, so it is possible to use an herbicide which is potentially toxic to our crops, and we can put safeners or protectants to widen the use of this chemical. How does the safener work? It may increase cytochrome P450, it could increase glutathione, or UDP glucose transferase. So the protectants or the safeners may stimulate biochemical activities which may lead to degradation of the herbicides, and by doing so the crop is protected. We now want to move on to something different. Now, when we apply our herbicides, let's say you are applying Fusilate, which is a post-emergence herbicide used in soybean. You also want to put Basagran, which is also a post-emergence herbicide. Probably you may think it is wise to mix these two so that you save on fuel. Yes, you can save on fuel, but what happens is that when we mix these two herbicides together, they are not going to kill the weeds. This phenomena is known as herbicide antagonism. Herbicide antagonism. It can happen with fusilade, and basagran. Both herbicides are used in soybeans post-emergence. You mix them, you get antagonism. And no weed control. Right? So they should be applied separately. So just remember that although it makes a lot of sense to mix these two and save on fuel, since they are both post-emergence herbicides in soybean, the result is that if you mix them, you get antagonism and no weed control. Therefore, apply them separately and make sure you clean the tank. The other issue is the herbicide synergism. Herbicide synergism. Now, in herbicide synergism, if you mix the herbicide and an insecticide, especially organophosphate and organophosphate one, you can kill your crops. This can happen with the herbicide nicosulfuron, which is sulfonylurea herbicide. Sometimes after application of insecticides, we don't wash the tanks and we simply put another chemical. This can actually cause a synergism. Let's say you are putting in herbicides. In fact, some people do mix insecticides and herbicides and do one spray in order to save on fuel. which is also problematic because it can kill your crops. So nicosulfuron plus especially phosphates, insecticides, you avoid to do this because there is going to be crop phytotoxicity. Although we know nicosulfuron normally doesn't kill the crop, phytotoxicity. There are some people who may mix, they may add a bit of ammonium nitrate to glyphosate to make it more toxic. This can also be an example of synergism. So I will quickly summarize what we have just discussed and then finish off this bit on selectivity, although we touched on some other important issues. So on this one, okay, so earlier on we talked about atrazine metabolism and selectivity, where we have the chlorinated triazines, where we have the chlorine atom, which is now replaced by an OH. And please remember that the catalysts or the enzymes needed is benzoxazinone or dimboa instead of cytochrome P450, and we form an OH or hydroxy triazine. This is the actual process, hydrolysis facilitated by dimboa, where you replace Cl with an OH. So there's also a possibility of any dealkylation, removal of the ethyl groups. Those can be removed, forming the amines, as we discussed this. Now in phase 2, that was happening, what we have been discussing was happening in phase 1. In phase 2, you have conjugation reactions, atrazine glutathione conjugations. The enzyme which is important here is the glutathione S transferase, which allow glutathione to conjugate directly with the atrazine. As a result, there is loss of herbicidal activity, and this is why maize selectivity is actually achieved. So this is the atrazine glutathione conjugation showing the actual molecules, and the glutathione S transferase facilitating this process. Again, this is the glutathione conjugation reactions simplified. We said we can convert herbicides from being non-toxic to toxic, 2,4-DB and MCPB, via the reaction known as beta oxidation. We can actually apply 2,4-DB and MCPB, and we leave it up to the weeds to convert it to toxic forms so that they get killed. Plants which do not convert these, survive. So this is an example of conversion of 2,4-DB to 2,4-D, which is the herbicide which is toxic. We talked about safeners and protectants in maize and sorghum. Normally, the type of herbicides belong to the group, the thiocarbamates, for example, EPTC, chloroacetamide, which is the metallochloroacetachlor. As we have said, EPTC is a safener known as the diclomid, which is already formulated in this herbicide to protect maize. Concept is also part of metallochlor. You can put it in sorghum, but nowadays it's formulated in jewel or metallochlor. That is the concept. This one is important because you may want to put a grass killer in sorghum. Make sure you have got jewel with concept, because there's another jewel without concept. It can kill your sorghum. Alacro, you have flurazole, which protects sorghum. Acetachlor, oxabetrinyl, which protect sorghum. So safeners can increase the metabolism of herbicides. They can increase the levels of glutathione and glutathione S transferase, or even P450 enzymes, so that herbicide degradation is fast in order to give protection. Antagonists, we said, although it makes sense to mix basagran and fusilade, which are both soybean herbicides, in order to save fuel, but if you do so, you are not going to kill it. So apply them separately, because they are antagonistic to each other. Synergists, nicosulfuron, if it is contaminated with an organophosphate insecticide, usually this happens when tanks are not cleaned properly. Tanks used during spray. Or people may just mix the herbicide and the insecticide together in order to save on fuel. Sometimes it works, but with the nicosulfuron, you may end up killing your crop. But some people do actually do it deliberately. Get ammonium nitrate, mix it with glyphosate in order to boost the killing effect of glyphosate. Well, it has been quite a long journey. This is the summary of selectivity, physiological based selectivity. We talked about differential penetration, differential translocation, compartmentalization, sequestration, altered binding site of enzymes, differential metabolism, which is phase 1, phase 2, and phase 3, conversion of herbicide from non-toxic to toxic form, which we've just done, safeners or protectants, antagonists, then finally synergists. Well, on selectivity, we are saying you can apply the herbicide. It can kill other plants leaving other plants alive. In this case, where MCP was applied, it could kill soybean and other weeds, leaving maize. This is it. So we've actually finished on herbicide selectivity. I'll stop here.